I want to take a look at number 4 on page 152. And this is the trajectory problem, right? And it's about a football being kicked. It says a player kicks a football from ground level with an initial velocity of 27 meters per second at an angle of 30 degrees above the horizontal. Okay, so they kick it this way, 27 meters per second. This is 30 degrees. And we're supposed to find three things. We're supposed to find the hang time. Okay, that's just the time the ball's in the air. We're supposed to find the range, which is how far the ball goes, which is really change in x, right? And we're also supposed to find the max height of the ball. Okay? How do we do this? Well, it's just like anything else. Okay? When we have motion in two directions, we have to split it up into its components. When we have force in two directions, we split it into its components. When we have motion, we split it into its components. So we have this side of the triangle, which is in the x direction, so this is v naught x. And we have this side of the triangle, which is in the y direction. This is v naught y. And so v naught x equals 27 cosine 30, okay? Because cosine, remember, is adjacent over hypotenuse, so that's v naught x, or the x side, over 27, and so to get the x side, we just multiply by the hypotenuse. In a similar fashion, v naught y is equal to the 27 times the sine of 30. Okay, so those are my components. How do I get those? How do I use those to get the hang time, the range, the max height? Well, the time is completely dependent on the y because where it starts, where it ends, and the acceleration in y are the only things that change, right? If we actually were to map out the trajectory of this ball, it starts, it goes up, it comes back down. And if we look at each point, right here at the beginning, it's moving up and right. A few seconds later, it's still moving up and right. A few seconds later, it's basically just moving right. A few seconds later, it's moving down and right, down and right, down and right. The thing that's common in everything there is it is always moving to the right because there is no acceleration in x. The acceleration in x is 0. Because if we just pick a point and look, there's only one force acting. Right here, gravity's acting. Right here, gravity's acting. Right here, gravity's acting. But that's the only force that acts. Okay, since it's down, the acceleration in x is 0. However, the acceleration in y is not 0 because there is a force there. Okay, but the net force in y is equal to ma according to Newton's second law, and so that means mg is equal to ma. M cancels, and we can see the acceleration in y is really just g, negative 9.8. Okay, so we can use that information together with what we just learned to actually figure out how long this thing is in the air. So we had our initial velocity, v naught in the y direction, was just 27 sine 30. The acceleration in the y direction is negative 9.8, right? It's pulling down. Initial position, it starts on the ground. Final position, it ends on the ground. Okay? And from that, I can get time. I'm going to use the second kinematic equation, which is y equals 1/2 at squared plus v naught t plus y naught. Okay? And I know enough information to solve here, right? Y is 0, negative 9.8 is acceleration, t squared, plus v naught, which is 27 sine 30, times t, plus y naught, which is just plus 0. Okay. So negative 4.9 t squared plus 27 times the sine of 30. Make sure your calculator is in degrees when you do this, but the 27 times the sine of 30 should be 13.5 t, and that equals 0. Okay, now you could use the quadratic on this, but there's no reason to, right? I can divide this term by t, I can divide this term by t, I can divide this term by t, and I get 0 equals negative 4.9 t plus 13.5. Okay, and so I can subtract over that 13.5, get 13.5 equals 4.9 t, divide by 4.9, divide by 4.9, and t is 2.76 seconds. Okay, so the hang time for this ball is 2.76 seconds. Now that was only one part of the problem. It also wanted to know the range and the maximum height. Okay, so let's go on to the maximum height. Okay, this is an interesting problem because I'm gonna redraw this picture, the trajectory again. Okay, the maximum height happens right here. Okay, which is half the time the ball's in the air because it starts and ends at the same level. It's symmetric. I don't really like that method. You can take the time you just found and cut it in half to get the maximum height. The problem is sometimes you start at a higher location than you end, or you end at a different height than you start, and so then that equation doesn't work. So what I like to do instead is go to the third kinematic equation, which says v squared equals v naught squared plus 2a delta y. Okay, and this works because you actually know the final velocity at the maximum height. The maximum height, the velocity in the y direction, is 0, right? Because it's not moving up, it hasn't started to move back down, it's just moving forward at that point. Okay, so its velocity in y is 0. Yeah, it's still moving forward, but it's not moving up or down. Okay, so then I can say, all right, 0 equals v naught y, which I just found to be 13.5 squared, plus 2, acceleration in y is negative 9.8, times the change in position. Okay, and so then 13.5 squared is a fairly large number, around 200, and 182.25 minus 19.6 delta y. Subtract that 182.25 over, divide it by 19.6, and we see that our change in y is 9.29 or 9.3 meters. Okay, so the ball goes 9.3 meters above where it started. Since I started on the ground, its maximum height is 9.3 meters. Okay, if I hadn't started on the ground, I'd have to either add or subtract my starting point. Okay, so it goes 9.3 meters high, and then the last question here is, how far does it go? Okay, well, I know the time it's in the air. The time it's in the air is 2.76 seconds. I know the acceleration in x is 0. I know the initial velocity in x is given by 27 times the cosine of 30 degrees, and I'm just looking for a change in position. How far does it move? Okay. Again, second kinematic equation. If we look at the first one, v equals v naught plus at, since the acceleration is 0, and the initial velocity and the final velocity are the same, I'm going to have 0 equals 0 plus, well, or v equals v plus 0 times t. So that doesn't really help me. If I go to the third one, v squared equals v naught squared plus 2a delta x. V squared and v naught squared are the same, and the acceleration is 0. That doesn't help me. But the second kinematic equation, x equals 1/2 at squared plus v naught t plus x naught, that helps me, right? X minus x naught is delta x, so I can subtract that over, equals, acceleration in x is gone, so this is just v naught t. Now I have to remember this is x, so I don't want the whole v naught, I just want the 27 cosine 30. So I take 27 times the cosine of 30 times the 2.76 seconds that it's actually moving through the air. So 30 cosine times 27 times 2.76 is about 64.5 meters. Okay? So the ball goes 9 meters high at its highest point. It covers a distance of 64.5 meters, and it's in the air for 2.76 seconds. Okay? Now, the next problem on here says to actually say, well, what if instead of kicking it at 30 degrees, he kicked it at 60 degrees? And I want you to find that information. Okay? What you should find is that the range stays the same. However, delta y and t are going to be different. Okay? Now I want you to stop and think about why 60 degrees and 30 degrees are going to end up with the same range. Okay? They're complements, they add up to 90. Okay? At 30 degrees, most of your motion is forward, and so it doesn't stay in the air for very long, but it's going really, really fast, so it can cover a great distance. At 60 degrees, most of your motion is up, Okay, so it's not going very fast forward, but there's a whole lot more time for it to move, so it's going to get to the same spot. Okay, where should you kick it in order to get the greatest range? What angle? Okay, what do you suppose that angle is? Think about that. Try these problems, and let me know if you are stuck on anything.